So, CS 170 is about algorithms, all right? And I know what's in your mind. What is an algorithm? What are algorithms? What do we have to learn them? What's going on? What's going to happen this semester? All right, so I'll tell you all about it. So, you look around you. The computers are everywhere. And using them, you can do incredible things. And the question is, how do you come here? And if you think about it, there are two reasons for that. There are two reasons. So the IT explosion has two roots. One is Moore's law. The amazing, staggering, exponential growth in hardware, okay? And the speed of hardware, the sophistication of hardware, and of course, architectural innovations, software, everything, all right? So these are all incredibly important. Couldn't have done it without it. And there is a second pillar, all right? That Moore's law wouldn't be able by itself to deliver what you see around you today. Okay, and the second pillar, and I hope by the end of this course you are going to be convinced, is what we call algorithms. And by algorithms, we mean, informally speaking, clever ways of using this hardware, okay, to do useful things. All right? So, so people tell me, I know how to code. Why do I need to learn algorithms? Okay, so is algorithms just coding? And it's a hard question because, in some sense, algorithms is just coding. Okay, so it's a subtle answer. I mean, I cannot explain it well without a metaphor, an allusion. Okay, so and it has to do with Asian martial arts. Okay, so I don't do these things, but I admire them immensely. Okay, so when you see somebody do it, I mean, it does incredible things, and it's sort of very agile, beautiful postures, beautiful motion, and so if you see somebody who's quite good at it do it, and then you watch a real master, a true master, sort of the best in the world do it, and superficially they seem to be doing the same thing, okay? Except there is one difference. If you watch closely the face of the good guy, not the master, the other guy, then what you'll see is that there is agony in his face. Okay, so so he's trying very hard. And when you watch a master do it, what you'll see is that the master does exactly the same things, but does it with a smile on his face. Okay? So this is what algorithms is. It's coding with a smile on your face. Okay. No. All right. So let's do some administration first, okay? I know you have many questions. How many of you are in the wait list? Okay, I have one word of advice for you. Wait. All right, so, okay, and things will happen. Don't worry. Okay, so you'll get in. Okay, so we were given a big class. Okay, we are going to have another section. Okay, or we are going to increase the number of sections. People will drop out. So you will get in. I cannot sign sort of a contract with you that this will happen because it doesn't depend on me. Okay, I have no say, and neither does Satish, on who gets in. All right, I don't know how many of you know this. Okay, but we don't. The department. Okay, there is an officer. There is a respected staff member of the department, sort of who handles these things. All right, and they will decide. But we will do everything we can so that everybody who wants to sit in this class can take this class, will take this class. All right? So don't worry about it. How about, so everybody who has been admitted is in a section, okay? There are going to be probably 7 sections, something like this. So people have asked, can I go in a section that is a little more convenient for my time? Okay, so fine. You can, usually we use hashing for sections. Okay, so basically you can go to any bucket you feel okay. Now, what else? Problem sets. So this class, like CS70, how many of you have taken CS70? Everybody, right? Okay, cool. Yeah. If you have not taken CS70, you better talk to us. All right? This class is going to have weekly problem sets. Okay? Like CS70, and even more importantly than CS70, these are crucial part. The problem sets are a crucial part of the class. All right? Because you really cannot learn algorithms, as in CS70. You cannot learn how to prove things, okay? But here you cannot learn algorithms. You cannot learn how to appreciate algorithms, how to devise new algorithms without working very hard, okay? So usually sometimes it comes as a shock to people how hard they have to work in the beginning, okay? And so be prepared that these are demanding problem sets, all right? But they have to be because they want to, in the end, they want to put a smile on your face, okay? So, so they're good for you, okay? So remember the martial arts analogy, okay? So what do I have advice for problem sets? Yes, absolutely, we have advice. First of all, don't do it by yourself, okay? By all means, at all costs, try to have a study group, okay? It's extremely important to have a study group, okay? If by the 3rd week you don't have a study group, please come to us, okay? Or find a study group, all right? It's very important that you do these things in a study group. The reason is the following, that you are going to spend untold number of hours working on problems, okay? 90% of these hours are going to be like sitting there and feeling miserable, okay? Waiting for the idea to come, all right? So think about it, okay? If 5 people sit together or 4 people sit together and wait for the idea to come, okay? Won't it come earlier? All right, so that's the idea, all right? So that, and then you start discussing it, you start refining it, okay? So this is how I think everybody should be working on problem sets, all right? Because that's how it works. There is one interesting innovation from CS70 that you are required to submit electronically. Okay, there are going to be only electronic submission. Okay, don't panic. It's easy, all right? All you can do, you can write in ASCII. Okay, so you can handwrite and scan. Okay, there are many ways. All right, so choose your way and do it. All right, we are going to be posting a homework every Wednesday, starting tomorrow. All right, and the homeworks will be due Wednesday, okay?
Posted Wednesday and due Wednesday
The next week, yes, right. We'll figure it out, so there will be some time, okay? And you have to press the send button by that time, okay? Do accept late homework, okay? We do not accept late homework, okay? But we do the following almost as good thing, okay? You always drop the worst 2 homeworks, Okay, you cannot drop the last homework, okay, because it's important that you do the last homework. But you can drop all homeworks, any 2 homeworks, and if you miss homework for some reason, okay, fine. Okay, if you miss 2, fine. It's still within range. Listen, if 3 amazing emergencies happen to you during a semester, losing 2% of your CS 170 grade will be the least of your problems, okay? So, all right. There is something else that I want to tell you about homeworks and about the course in general. You can work with other people, okay? You can listen to the ideas of other people and use them, okay? But then after your study group meeting is over, you can do something else. You can look at the web for solutions. Fine, okay? You know, it's a rich universe these days, okay? So and you can do anything you want. You can skim Wikipedia. You can do anything you want, okay? Except that when you write your homework, I want you to tell us exactly what happened, okay? That we worked in a study group, and this idea actually came from this person, okay? That's fine. You'll get absolutely full credit, but it's a useful exercise, that in this business, when we are dealing with matters of the intellect, we have to be absolutely honest, okay? Or I found it in this website, okay? I found the answer to this website. That's excellent. You get full credit. Because in real life, when you have to solve a problem with coding, with algorithms, you are allowed to ask a friend. You are allowed to look at the web. Okay, you see my point? So that's absolutely fine. That's within the rules. Everybody knows what Piazza is? Okay. So we do that. Now I know. Okay, so as of this morning. Okay, so yeah. One little thing that I have to tell you about homework and about exams and about all these things. You know Satish, we are Satish and I are really cool, nice guys. Okay, so we really like students, and all that. Okay, the point is that there is only one thing that turns us into Mr. Hydes, okay? And that's academic dishonesty, okay? So don't copy homeworks, certainly, of course, not exams. So always we want the homework that you turn in to be your work, okay? All right? My office hours are going to be Monday, 5 to 6, okay? You'll know that. And sorry? My office is Soda 689. 5 to 6, yeah. We're going to follow a book in this class, okay? This book is by Dasgupta, Vazirani, and a guy named Papadimitriou, okay? So it's, I'm sure it's in the bookstore. I also know it's on the web, okay? So you can, if you want, you can look at it on the web. I want to tell you something, the reason we put it on the web is because we wanted to save trees, okay? So every time I see the book printed, so the downloaded and printed, sort of my heart breaks, okay? So all right? Yeah. They're a little different, yes. Most significant, but if you don't want to buy the book, you'll do fine with the web. Sometimes the numbering, that's the most annoying of all. Sometimes the numbering of the exercises is different. So in our exercises, when you assign exercises from the book, we are going to say 5.3 parentheses, it starts like this, okay? So, you know, let x be, and so on, so that you know how to find it, okay? So there are going to be 2 midterms and a final. Make sure the dates of the midterms are going to be posted sometime this week, maybe tomorrow. The date of the final is already known, okay? So make sure that you can take the final before taking this class. Yeah.
Are you posting things on Piazza to give us updates?
Yes.
What about the course website? Is that useful?
There is, yes, you know, Satish, what do you think? What you know, between the Piazza and the course website, the Piazza is much more informative, right?
Yeah, just take a look at two.
Yeah.
Piazza will have everything, but the website also has.
Yeah. So once in a while, make sure that you know what's on the course website. Okay. But Piazza will not let you forget it. So. People usually ask us what is the breakdown of grades, okay? And the default we are using is 20, 20, 30, 30. 20 midterms, 30 final, 30 homework. Okay? All right.
Did you say where to turn in the homework? Where to turn in the homework?
Oh, electronically.
Oh, okay.
Okay. And all right. For this we need some kind of secure system, and for this reason, during your first, make sure you go to the first section. During your first section, you are going to get a form, all right, where you can register to the secure system that we are going to be using for submitting homework and for assigning grades and all that. Okay, so you have to do that. I mean, without it, you'll have trouble turning the homework next Wednesday. Okay, so make sure you go to the section and you get the form. Any questions? Can't believe it, I covered everything. All right, so let's start talking about algorithms. And in fact, I think that maybe we should start from where it all began, okay? And so how algorithms started is a long story. Do you know what algorithm stands for? Where the word algorithm, it's a strange word, right? I mean, where did that come from? It comes from a person, his name was Al-Khwarizmi. Who lived in Baghdad around 900 AD. And this guy essentially discovered algorithms, not quite. Yeah.
Oh, sorry, I don't know if I missed it earlier, but do we have discussion this week?
Yes, of course, yeah.
Okay.
Yeah. Yeah, there are going to be discussion sections this week, and be sure to go because you need to get these forms, okay, and register. Forms with instructions how to register. Okay, so people were always interested in algorithms, and in the beginning, algorithms had very specific meaning. They were the first algorithms, actually the only algorithms until recently, until 100 years ago, were the algorithms that we learn at school to multiply decimal numbers, okay? These were the first algorithms. They sound like mundane and stupid and boring, but it's amazing what an incredible advance they were, okay? Because you see, before that, people were representing numbers like this. You know, to write 87, you would have to write this. Okay? 50 plus 10 plus 10 plus 10 plus 5 plus 2 plus 2, okay? And the question is, how do you do this? How do you multiply 87 times 91? Okay? You don't. All right? So this was a huge problem, okay? You know, and basically there was a case, a clan, sort of, you know, the abacus experts, okay, who were basically doing this for people, all right? So, you know, then in some place in India, they came up with this idea, all right? That we only have 9 symbols plus the world's most important symbol, the 0, okay? In India, they used a dot for 0, okay? And when it came to the West, that's when the 0 took its today's form. So the idea came, why don't you do this? This way, they found out that you can do actually operations, okay? You can add them. You can line them up and add them. You cannot line up these guys, okay? Basically, and there is no end to it, okay? There's no reason why stop at 1,000, okay, as the Romans did, okay? Because you can go way up, okay? You can just recycle digits, okay? And you can have as many digits as you want. So the Indians knew by, I guess, 700 AD how to add and multiply numbers. Incidentally, the other civilization that came up with this around the same time is which one? Do you know? The Mayans. Sorry? Okay, the Mayans. The Mayans came up with a very similar, with a positional system, okay? That's something to remember. The interesting thing is that they had, their basis was 20, not 10, 20. You know the reason is. The reason is that the Mayans wore no shoes, okay? So they could see 20 things, okay, to count it, right? So, all right? And then, after a few hundred years, Al-Khwarizmi, who was like the wise man of the court of Baghdad, okay? Then it was a big power. He heard from dealing with, I guess, merchants from India. He found out about this amazing idea and learned their algorithms. He invented a few by himself, sort of, you know, like how to find the square root of numbers, how to compute pi. So, you know, he was the first guy who did all this, and wrote a nice book, a nice textbook, okay, that to explain this to people. And it took 400 years for this textbook to be translated, to arrive in Europe. But and then it was I mean, it was not easy because it was, you remember, this is the Middle Ages, right? I mean, and the church is very, very powerful, and it was branded infidel propaganda, okay? So that algorithms were, you know, so what, but it took a lot of effort and a lot of, I guess, leadership from a few people for this to spread in Europe, okay? And it was, it spread, it was a difficult, amazing. In England, there was a lot of resistance, apparently, from the abacus union. Okay, so they didn't want the new thing to, they would run them out of business, and they negotiated with the king that the state finances will always be done by abacus. Okay, so do you know how the finance minister of England is called? It's called the Chancellor of the Exchequer, and the exchequers were the abacus. So basically they, even in today's English bureaucracy. So the nomenclature says that there was a resistance against the algorithms, innovation is never easy. So in any event, now we have this, and we know how to multiply numbers. Okay, so and we learn this in second grade, and it's amazing. All right, so but it's unbelievable how much blood has been shed by and how much effort, how much sweat has gone into doing this. All right. In any event, we all know how to multiply numbers. Okay. Do you know how the French multiply? How the French multiply numbers? You won't believe this. So imagine that you want to multiply, I don't know, 37 by 78. Okay? How do you do it? Easy. You do the 37 by 78, 6, and so on. Okay? Right? You know how the French would do it? They would write them like this, okay? Then they would do the following. They would have that, and they would double that. They would have that, and they would double that. They will have that, and they would double that. They would have that, and they would double that. They would have that, and they will double that. Okay? And now what they do is they pick out all the even numbers here, and you erase these lines. And then they add these. Do you believe this?
Wait, do they still do that now?
Sorry?
Do they still do that now?
I believe so. That's how French kids learn how to multiply in school. I'm pretty sure about that, okay? In any way, that's what the book says, okay? So all right? So, is this correct?
Yeah.
It's correct, okay? So we'll find out why. All right, so let's, everything all come in good time. So, I told you that I was in the middle of the story of algorithmic. You know what's the name of I told you that it took a lot of leadership by a lot of clever people, by a few clever people, to bring his wisdom to Europe, okay, and then the world. And what was the name? You know, what's the name of one of the leaders in this? One of the most fervent supporters of the position of the decimal system and algorithms. His name was Fibonacci. Okay, he was an Italian. He lived in Pisa. He was a mathematician. And very early, he learned about algorithms. He read Algorithm's book, and was very interested in propagandizing algorithms. Of course, Fibonacci, now you know him from something else, right? The Fibonacci numbers. all right? And you know what they are. They are okay? They are computer science's favorite sequence or number sequence, right? After the powers of 2. Okay, so these are Fibonacci numbers. And of course, you know what they are, that f1 equals f2 equals 1, and fn is fn plus 1 plus fn minus 2, where n is greater than 2. Okay, so that's the definition of Fibonacci numbers. Okay, nothing new here. And just as a silly warm-up in understanding algorithms, I'm going to write on the blackboard algorithms that compute the Fibonacci numbers, all right? And I think you have seen this before, okay? You have seen, you know, in the beginning I'm going to do something, I'm going to follow my face, and then I'm going to recover, okay? So that's what's going to happen, all right? So, one first idea, of course, fatal idea, is to use recursion, all right? You must have seen that. Okay. So how do you use it? You say fib of n. If n is less than 2, less than or equal to 2, return 1. Else, return fib of n minus 1 plus fib of n minus 2. Right? That's an algorithm. All right? Incidentally, we are going to write algorithms using this notation, okay, informal notation. We are never going to actually define, you know, you are never going to see a manual of this programming language, okay? So, you know, it's basically, it's a way of communicating. But I hope it will always be clear. So, what's my point? My point is the following, that whenever in this class we're going to discuss algorithms, we're going to talk about algorithms. And algorithms are going to be our object of study, all right? Algorithms like this. And what we're going to do, how we're going to study algorithms. The basic idea, the bottom line is we're going to be asking 3 questions of them, okay? The first question is, most important, is it correct? Okay? If it's not correct, then we shouldn't be interested in it, okay? So, you know, if it does not solve the problem, then why should we study it? So that's the most basic question we're going to ask. Is this algorithm correct? All right? The fact that an algorithm is correct is, strictly speaking, a theorem, okay? Theorem, this algorithm solves this problem, okay? It's a theorem. As a theorem, it has a proof, okay? So in many ways, in this class, we're going to be looking at proofs that the algorithm is correct, all right? But you'll see how it goes. We are not going to make our proofs like incredibly formal, okay? I mean, so this is not CS70, all right? I mean, so we have come a long way since then. What we are going to do is we are going to give a perfectly rigorous argument why the algorithm works, okay? So here's the secret, all right? I mean, many people ask me the following. How much detail do you want in the proof, all right? That's talking about homeworks and exams. That's an important question. So here's what I tell them. Every question you ask them, chances are there is only one idea in the answer, okay? There is one idea why this algorithm is correct, okay? There is one idea why this algorithm takes so much time. every proof in this class is based on one crisp idea. If you get this idea and you write it down, you get full credit. If you don't get this idea, chances are that you are going to be compelled to write a couple of pages, okay? If these 2 pages don't contain this idea, they're a waste of time. Is this clear? So there is always one crisp idea why algorithms work, okay? Here it's actually very mundane, okay? It works because it implements the definition, okay? Sure, fine, okay? But usually it's going to be something slightly clever, okay? So you have to think a little about the algorithm, about the problem in order to understand why it works. Once you understand it, you can really convey it in 2 lines, okay? You don't need more. If you don't understand, if you don't get this idea, no number of pages will be enough, okay? So remember this when you write down. If you find yourself turning the page, you should stop and think, did I get the idea? All right? All right. So is it correct? That's the first important question that we're going to ask. And the answer here is yes. It is correct, because it implements the definition. Okay, it faithfully implements the definition. What's the second idea? What's the second question? How long does it take? How long does it take to run? Okay. Here, we have to explain things. How long does it take to run where, on which computer? Okay. As you know, computers differ a lot. All right. I mean, and even if we agree to count steps on a computer, I mean, a step could be a fetch, could be a memory fetch, and this, God knows what's going on. Okay. So, or it could be just a simple logical operation. So we only count what we call elementary steps on a computer. All right? And we don't care about differences between computers that save you a few nanoseconds in a few. All right? Because if we were interested in that, we would be in trouble. Okay? The problems we are going to face are messy enough. Okay? If we didn't have a very simple model to think about, which is basically is we only count elementary steps on a computer, okay? And with practice, you will understand what you mean by elementary steps. For example, that's an elementary step. That's an elementary step. Maybe that's an elementary step, or forget it, okay? Maybe not. And it doesn't matter. We'll see why. Okay, so what is the, how long does it take? So here is a, in this class, we'll develop a methodology for answer this question, okay? One element of this methodology is first of all, okay, we count steps, all right? I neglected to tell you something. And then we'd say what answer do you expect? Do you expect an answer like 7, 70, 1,000? No, you expect a function, all right? We count the steps and then you express them as a function. As a function of what? As a function of the input. Because how much an algorithm takes depends on the size of the input. Here, let's say the size of the input is n, all right? So we want to see how much it takes as a function of n, right? And how long does it take? In order to answer this, here is a neat way to do it, especially for recursive algorithms. For recursive algorithms, we have a very nice methodology that is going to work, and the next few lectures are going to see lots of it. For recursive algorithms, the way we do it is the following. We say, let t of n, t, get it, time, okay? T of n be the number of steps, the time it takes for the algorithm to run when the input is n. Clear? Very natural. And then you write an equation for t of n. What is T of n? T of n is the following. If n is greater or less than or equal to 2, T of n is 1, right? Why? Because let's say this is one instruction. And otherwise, T of n is what? Is T of n minus 1 plus T of n minus 2. I guess plus 1 because we have to do this if, all right? And my point is, get it? There is an eerie similarity between this equation and the definition of the Fibonacci numbers. You see what I'm saying? That's a recursive definition of T of n. That's a recursive definition of the Fibonacci numbers. If I omit this, they're identical. Right? So what's the bottom line? That to compute a Fibonacci number with this algorithm, it takes time which is at least equal to that Fibonacci number. Okay? Which is not good. Right? Why is it not good? Here is why it's not good. Because how big is the nth Fibonacci number? Okay, suppose that we wanted to do f of 1,000. Should be able to do that. F sub 1,000, I meant. Yeah, so you is fib of 1,000. So what happens if you compile this and run it? You wait, right? Why? Because how big is the nth Fibonacci number? Do you know? F sub n is about what? Unless I'm mistaken, it's something like 2 to the 0.7 times n. Okay? Therefore, fib, let's be modest, 100. Fib of 100 is 2 to the 70. What is 2 to the 70? 2 to the 70 is a week, okay? 2 to the 700 is, don't ask, okay? But is this clear? So, the interesting thing is that Fibonacci numbers are exponential, all right? And if, you know, if you want to remember one thing from this class, it is that exponential algorithms bad, okay? All right? So that's an exponential algorithm because it takes that much time. And those of you who remember from 61A, you know why it's exponential, because it does the wrong recursion, right? I mean, the recursion, it keeps calling itself, it keeps calling the same functions again and again and again and again, okay, with the same arguments. Remember that? You understand why this is bad, right? Because it, you know, f of 3 is going to be called an untold number of times. Okay. So that's the first question that we are asking. How long does it, that's the second question, how long does it take? And here we get a disappointing answer. And the real question is, can we do better? That's the third question. And as you know, the answer here is sure. And it's the following. So, you know, you define F an array, and you do okay? You write this trivial algorithm, this trivial program, and this gives it to you. Because this is much better. How much time does this algorithm take? That's easy, n, right? Why? Because it has this, actually n minus 2. But hey, who cares? N, right? Let's say order of n. N, same thing. Which, of course, is much, much better than this terrible exponential. Yeah.
For something like addition, when you have larger numbers, how can you say addition is elementary? Because larger numbers want to take a proportional.
Okay, he stole my thunder. Okay, so this no, yeah, you're absolutely right. This is not right. Okay, n is not right. It's not the right answer. Why is that? And the reason is that I told you already that the n Fibonacci number has n bits. Okay? So if you want to compute, I don't know, the 1000 Fibonacci number, then after a while, you are going to have a fixed point in the integer overflow, right? And so you'll have to do large number. You have to download a large number package, right? I mean, that allows you to do addition with 1000-bit numbers. Not a big deal, but you have to do it, all right? And as a result, every operation is not one elementary operation, but it's about n elementary operations. You see why? Because if you have 32 bits and you want to compute the millionth Fibonacci number, right? Then the millionth Fibonacci number is going to have 700,000 bits. By 32, it's about 20,000. Okay, so you really have to do about n operations, because addition, as we're going to see, it takes, to add two n-bit numbers, takes n operations. And so the real answer is order of n squared. Okay? Did I go too fast over this one?
Yes.
Okay, okay. So here's what I'm saying. That we have to be, so the only thing I want you to remember is that we have to be sometimes a little careful what to mean by elementary operation. Because now that we know that we have huge numbers to deal with, these huge numbers cannot be dealt as an elementary operation in our computer, okay? Actually, frankly, the first couple of lectures are the only parts of this class where this is an issue, all right? Because after that, we are going to use operations with numbers, but all our numbers are going to be small, okay? You know, because why? Our numbers are what? Maybe our numbers are, I don't know, are indices of nodes of a graph, okay? How many nodes can a graph have, okay? to be of interest, okay, so, you know, we can have at what, you know, 1 trillion nodes at most, okay? Because, I mean, you know, how many people are in the world, okay? How many files can there be in the world, okay? So, you know, there are limits to these things, and it's very reasonable to assume that we can fit everything within the 64 bits, let's say, of an enhanced multiplication and addition. But for these couple of lectures where we sort of, you know, we look into arithmetic operations, we have to be a little more careful. And this consideration gives you an extra factor of n here, because these numbers are going to have about n bits, and so to break them into 64 segments of 64, you really have to have about n, well, n over 64, okay, n. Right. Incidentally, I've been using this notation, order of n. And when I say order of n, what do I mean? I mean the following. What I say n order of n squared, I mean the following. That I have put a lot of effort into analyzing an algorithm, and in the end, I found out that the number of elementary steps of this algorithm is something like 2n squared plus 11n plus 43. Okay? N, order of n squared. Okay? We don't care about this because it's dominated by this. We don't care about this because it's dominated by this and this. I don't care about this because, I mean, if I care too much about this, why don't I go and buy another computer which is twice as fast, okay? You know, and right? Or why don't I wait 3 months? Right. Okay? So that's how this comes out. Incidentally, one of the problems is, you know, one of the things, sort of, it's a new kind of calculus. One of the things we have to get used to is to be able to eyeball a function of n and immediately say where it stands in the realm of all functions of n. Okay, so your first homework is going to contain a problem where we give you something like 20 functions, n squared, 2 to the n, n factorial. I tell them order them. Right? So you'll see tomorrow.
Question?
Yeah.
I'm still unsure how you're getting, how that algorithm is n squared.
Okay.
You're doing for each got ones. I mean, you've got everything in a map or an array.
Right.
Doesn't that cost a time lookup at that point?
Right. The point is that this is not an array of int. It's an array of long int. All right? Okay? Yeah.
Why isn't addition log n?
The addition is log n, where n is the number of bits. But the number of bits here, right? I'm sorry. Addition is log n, where n is the number, okay? Addition takes the number of bits. The number of bits here is n. Okay. Right? The number of bits of the nth Fibonacci number is about n. Thanks. This is, I mean, no, I don't want anybody to be confused about that. Okay? You get it? Okay. Okay? That Fibonacci number is a huge number. The nth Fibonacci number has about n bits. 70% of that, but that's n bits. Okay, so the log of the Fibonacci number, which is what we are saying, is n. Okay, so basically the logarithm of numbers we have to deal with in this algorithm is going to be n. That's why n is shows as a multiplication. Okay. Any more questions about that? Yeah. Excellent. So So you see what your colleague is asking? Do we deal with parallelism? And that's a wonderful question, because by the time you are going to be working for 10 years, okay, the computers are going to be incredibly parallel. Okay, right now we have parallelism in our computers, but I mean, it goes up to, I don't know, 64. But soon it's going to be like in the thousands. And we will need to learn about how to write parallel algorithms. And for the first time in this class, Satish and I are going to tell you about parallel algorithms. Okay, so we are going to deal a little with parallelism. Okay? Yeah?
Are we also going to deal with quantum algorithms?
I doubt it. Maybe in the end, sort of, maybe we'll have a lecture about quantum algorithms. Okay? If you are interested, the last chapter of the book is about quantum algorithms, so you can read all about it anytime you want. Okay. All right. So, and there is a question. Okay. So, the question number 3 is not asked once. Okay, it's asked every time. Right? It's a recurring question. Can we do better? Well, what do you think? We can do a little better. We can do a little better. In one of the problems in the new problem set shows you that you can really do a little better. Okay? So very surprisingly, you can do better than this algorithm. Okay. So, as I said, we want to think a little now about arithmetic operations. Okay, just as a homage to Al-Khwarizmi and Fibonacci and the people sort of who brought us the algorithms for multiplying and adding numbers. So, from now on, n is no longer going to be the input parameter to Fibonacci, but it's going to be the number of bits. Okay? So how long does it take to add 2 numbers with n bits? N, exactly. Yeah, no doubt about it. Good. Multiplication. How long does it take to multiply? Can you do better than n? You can do better than n. Here is why you cannot do better than n, okay? In order to add 2 numbers, you should at least look at the 2 numbers, right? Clear? And looking at these 2 numbers takes n time. So you can't do better than order of n. How about multiplication? How long does it take to multiply 2 numbers? You have thought about that? If you have n-digit numbers, now think decimal digits. A 7-digit number, okay, in the millions, and an 8-digit number in the tens of millions. How long will it take you to multiply them? What's the complexity of the multiplication algorithm you learned in 3rd grade, I guess? Sorry? N by m, exactly. So if you have 2 n-digit numbers, what's the answer? You see, because you are going to do this adding, but I mean, you are going to have to add n numbers, right? I mean, you have to. So multiplication takes order of n squared. And how about division? By division, I mean div and mod, okay? Also n squared. Long division takes n squared. Everybody believes that? So we're not going to insist on that. But believe me, and if you don't believe me, think about it for a minute. Long division is an order of n square algorithm. Okay, because as the numbers get very long, in the end, you really have to do a lot of multiplications, and this is going to dominate the division. And there is a cute, if you want to look at the textbook, there is a cute recursive division algorithm which convinces you immediately that it's an n square algorithm. Okay. Okay. Now I am going to mention a subject that I bet you that a lot of you had hoped you will never see again. Okay, that's modular arithmetic. Okay. Because I'm going to talk about exponentiation. So addition is x plus y, multiplication is x times y, exponentiation is x to the y mod z. Because exponentiation without mod is, first of all, meaningless, okay, because you really create huge numbers that you don't know how to handle, okay? You see what I'm saying? That if these are n-bit numbers and you don't have mod, how many bits does this guy have? This has n bits, this has n bits. How many bits does x to the y have? This one, if this has n bits and this has n bits, this one is going to have how many bits? If you keep going, you'll get it, right? Right. So let's think, all right? This one has n bits, all right? We want to multiply it by itself. How many times? Y times, which is what? Which is like 2 to the n. Every time I multiply it, I increase the number of bits by n. Right? So in the end, it's going to have 2 to the n, that's how, times n bits. That's a lot of bits. All right? So if you want to exponentiate two 32-bit numbers, you are in trouble. So that's why we have this mod z that makes it into a meaningful operation. Okay? Not only meaningful, but useful for RSA. Right? This is basically what happens in an RSA chip again and again and again.
Question?
Yeah.
Mod z makes the term x to the y meaningful?
Yes, because why is that? Because it tells you no matter what, we are going to stay within n bits, mod z. Okay, so we are going to do everything modulo z. So we're going always to stay with numbers that are less than or equal to z. So we're going to be fine. It's like it tells you, don't worry about x to the y, it's fine. Okay, so we're going to keep it small. And coincidentally, this is what we want to do. Okay? We want to, the useful thing to do is exactly that, exponentiate modulo z, because that's what is done in RSA. You have done RSA, right? And if you remember, that's what you do there. You exponentiate modulo a number. Anybody remembers how do you exponentiate? What's the clever way to exponentiate? Sorry? N cubed. Yes, it takes, if these are n bits, it will take in the n cubed operations. But what is the method? Repeated squaring, right? You remember how? You want me to tell you? Or I'll remind you. So imagine that you want to raise 213 to the 87th power modulo 900. Okay, for example. How do you do it? Easy. You take 87 and you write it in binary. Okay? That's 64, no 32, a 16, no 8, a 4, a 2, a 1. Right? That's sorry. Right? That's 87. Okay? And now you do the following. You take, what do you do? Now what you do, you multiply 213 by itself, modulo 900, so you keep it small. And then you take the product, I don't know what it is, and you multiply it by itself once more, and so on. So you create 213 square, 213 fourth, 213 eighth, 213 16th power, 213 32nd power, 213 64th power. And now you pick up this, this, and this, which is basically exactly the ones of this binary expansion. And you multiply them all together. Okay? Yeah. Yeah. So what does it say? It says the following, that I want to raise 213 to the 87th power. I want to raise it to this binary number. Okay? So it means that I want to take 213 and multiply it by 213 squared, because that's 2. Everybody sees that? 213 to 87, it is 213 times 213 squared times 213 to the 4th power times 213 in the 16th power times 213 in the 64th power. Is this true? That's what this says. Right? So all I have to do is create these guys and then multiply them. That's what I did. Is it better now?
Okay, what I don't understand is, so you're doing the multiplication part over here, and you get two, left-hand side, right there.
Here.
You get two products, like two lines, and you multiply those together, and that's...
No, I get one product, which is 213 to the square. Right. I forget what it is, maybe I don't know what it is. And then I multiply by itself. Okay, and then you get the 4th. And then the 8th, then the 16th. That's called the repeated squaring, okay? You want to see a very cute way to do it, okay? Much less messy? Tell me if you like that one more. It's a function x, y, z, okay? And does exactly this. It computes x to the y modulo z. Okay? How am I going to do it? It's very much like this. You'll see how. If y equals 1, return x. Okay? Sorry? X mod z, yeah, x. X mod z, sure. Else, do the following. R is x to the y div 2 mod z. Y div 2, of course, is exactly this, right? The integer part of dividing y by 2. Remember? That's what we are doing here. Then, if odd of y return r times x, else return r times r. Tell me if you believe it. This is the exponentiation algorithm. It's a recursive algorithm. It says if the exponent is 1, I have no work to do. Okay, that's how every recursive algorithm starts. If the exponent is not 1, then I divide the exponent by 2. Okay? If the exponent was even, then all I have to do is square the result. If the exponent was odd, then I have to stick another product of x. And I guess I forgot to say mod z everywhere. Do that make sense? Do that make sense? No, no. It's, okay, watch, okay? I'm not, so he's asking, is this exactly the same algorithm as I had before? We just, with all this sort of repeated squaring, or it's something else? I don't know. It depends on your point of view. In some sense, it's the same algorithm. Strictly speaking, it's not. It's a different algorithm. It's an unraveled algorithm, right? I mean, it's the difference between recursion and iteration, right? That was an iterative algorithm. This is a, in some sense, the difference between these two algorithms is exactly the difference between the algorithm for integer multiplication you learn at school and the algorithm for integer multiplication the French kids learn at school.
Which one performs better?
It's exactly the same. It's like you unravel the recursion, so it will not change anything.
So they're both correct and
They're both correct, and they both have the same, which we are going to analyze now.
Can we have to have both, or do we have?
Listen, I hope that you will never be able to forget them. Okay. Okay. Sorry? Can you? No. Sorry? Can you do better than that? The answer is yes, because you can do better in multiply. You can do multiply faster. Okay. Are there any questions?
Why don't we care about space?
We do care deeply about space. Unfortunately, there is no time in the course to care about space, okay?